Okay, we're here at chapter 11, rolling contact bearings, and let's get to it. I found this online. Looks like an older chart, probably hand drawn, even the words, judging by how old it looks. But I thought it was really neat. Has a really good classification tree for bearings for rotary motion. We're dealing with rolling element bearings. The key thing is that these are rotary motion bearings. There's all sorts of linear bearings and things of that nature. We're dealing here in Chapter 11 with rolling element bearings, and Chapter 12 with sliding bearings. Chapter 11, that's going to be, I got to disconnect my keyboard again. Ooh, this sucker's on there. Chapter 11, this is going to be lecture slides and a video. This is chapter 12 is actually going to be PDF reading. Now, don't mind the small child sounds in the background. The wife is sick, so I said small child, he said small child. He's kind of mirroring everything I'm saying in the background, so it's not an echo one octave higher. It's actually, now he's saying bearing. You're a pretty funny little fella there. Anyhow, usually the wife takes over babysitting while I record lectures, but she has a pretty bad cold right now, so we're all going to just have to deal with it. Anyhow, I was talking about chapter 12. The reading assignment is posted on Blackboard. There will be no video or lecture slides. It's just the PDF files, so make sure you read those. So at the conclusion of this video lecture, we should be all the way through the end of chapter 12 if you do that reading assignment as well. Okay, we're not going to cover all this or in as much depth as the book in some cases. So instead of Xing things out now, I'll get to it through this lecture, what we're actually covering and what we're not covering. This one is important. This one, this is one of those ripe figures for multiple choice, true, false kind of questions on the final exam. Basically the parts of a basic ball bearing: inner radius or inner ring, outer ring, shoulders, rolling elements, separator. It's also called a cage. I believe I added this, but it's usually called the cage. Anyhow, the bore and outside diameter, all these things are important to know about basically the geography of a ball bearing, so make sure you're familiar with that. Here's a bunch of different types of ball bearings. Deep groove, this is probably the most common. And filling notch, my PhD was in rolling element bearing fault analysis, and I've never seen a filling notch bearing in my life. The main two I've seen out of this are deep groove and angular contact. Definitely a whole bunch of those. Definitely shielded and sealed. Usually shielded, sometimes sealed. This external self-aligning, double row, self-aligning, thrust, all this stuff on the bottom. This entire row is a lot less common. If you're just talking about ball bearings, you're usually talking about a sealed or shielded. You're usually talking about a shielded deep groove ball bearing. If you're designing a bearing for something, you're probably looking up a catalog for a shielded deep groove bearing. So a combination of A and D. Sealed implies that there's some other mechanism that's been designed in that does not necessarily come with the bearing. in this configuration shown for E, they have the actual bearing itself is sealed. Um, that's pretty rare. Usually they're just shielded, something to keep the grease in. But anyhow, deep groove and angular contact, A and C, pretty common. Angular contact are usually a little bit more heavy duty, so they might be oil lubricated. Deep groove are usually shielded, packed in grease, and good to go out of the box. A bunch of different types of roller bearings. There's straight cylindrical, spherical roller bearings, tapered rollers, needle bearings, uh, tapered roller for thrust, and steep angle tape. They all have steep angle tapered roller. These all have their own specific applications. I've seen a lot of needle bearings. Obviously, I've seen a lot of roller bearings in general. Usually, I've seen a lot of tapered roller and needle. Needle bearings, these are used for like light load, high precision applications. And tapered roller are used for more heavy duty radial and axial loads. So D and E are out of these, all these configurations, D and E are probably the most common that you'll see. One is for light load, high precision, and that's D, the needle bearings. And E, tapered roller, is more for, I would say, heavy duty combined radial and axial loads. Okay, bearing life definitions. Definition of a bearing failure: a pitting of an area of 0.01 inch squared. When that pit occurs, it's called a spall. And this goes back to chapter 3, Hertzian contact. Let me start that over again. If you remember, there's a reversing subsurface shear stress, and that causes a crack, a subsurface crack. And eventually that turns into a pothole. That's not technically speaking, and that pothole equals a spall or a pit or a defect, whatever you want to call it. It's usually called a spall. Once it starts to spall in a measurable manner, the bearing is done, and that one little spall will very rapidly turn into thousands of spalls and a lot of noise, heat, and vibration. So when you start hearing the degradation of a rolling element bearing, it's imperative that you keep on top of it, because they can accelerate in failure extremely rapidly. The life is the number of revolutions or hours required for a failure for one bearing. A rating life, this is usually the life required for 10% of a sample of bearings to fail, usually called the L10 life. So when they say L10, that means the life at which 10% of a sample of bearings fails. And then less used, by the way, this is very much used. The L10 life. Median life, not used so much. It's like the average life, it's 50%. It's the average life required for 50% of the bearings to fail. Obviously, that's not usually a good thing to happen when 50% of them fail. Might be good to know, but it depends what kind of design you have. And this is generally, you can just usually approximate it as 4 to 5 times the L10 life. Load rating definitions. Catalog load rating, this is the most important one. This corresponds to a constant radial load that will cause 10% of a group of bearings to fail at the manufacturer's rating life. Now, how does that differ from L10? Uh, L10 is for a group of bearings to fail in the field. Usually, the C10 life is based on an accelerated life test. So instead of 20,000 hours of actual life, they'll only test it for 1 million cycles, which might only take 10 minutes. So the catalog load rating, they can't take 20 years to test a set of bearings. So they accelerate the life testing and come up with a catalog load rating based on the accelerated life that they find of these bearings for different radial loads. And they wait for 10% of them to fail at a really high load. And the C10 life is used, you'd never actually subject something to the C10 life load, but you use that to select bearings for a much longer load. And there's correlation. So there's basic load rating and all these other definitions in here. Like I said, these things are reference value, and you'd never actually use these, not an actual load. You'd never actually use these loads on these bearings. Static load rating, this is again another sort of made up, not made up, but calculated or measured thing that you'd never do to a bearing. It's a static radial load that corresponds to permanent deformation, something you never want to have happen on your rolling element bearing if you can help it, over some theoretical contact patch. And this again is used primarily in calculations. You're not comparing this to the static load. So the static load rating does not equal your design static load. C10 and C0 are used in equations to determine what catalog rating and static load rating you need to use, but your actual load, static and dynamic loads, will be much different than C0 and C10. Equivalent load down here. This is for a bearing that has both, how we'll be using it is for a bearing that has a axial load and a radial load. So FA and FR, that's axial and radial. And what we'll be using F sub E for is essentially calculating an equivalent radial load for a bearing based on what the actual required axial and radial loads are. So load life relationship, keep in mind this is a log scale. And when you look at force versus life in a log scale, it's pretty much a straight line, which in the log scale gives you that equation. And this is used, I just want to call this out. So this here is used in a book example that we're covering. I think it's the first example maybe that we're covering out of the book. Specifically, suddenly A equals 3 shows up, but this is where it came from, just for future reference. So we have a load life relationship. This is mostly based on experimental. Let's go back to this slide. You see all these little data points? These are manufacturers' tests, actual tests, right? So they find the load life relationship, and it generally works out to be something like this. Now, not all of my scripts came through in follow-on slides. We have regular L's and script L's. They're okay on this slide. For some reason, they did not come through when I converted this to OneNote on follow-on slides, so I'll try to correct it as I go along. But this equation right here is going to be used, so that's important. Now keep in mind you're not always, sometimes the C10 is given and you're trying to find how many hours it's going to, like this would be how many hours you need, right? I'm sorry, this would be how many revolutions you need. Let me make sure I got that right. Yeah, that'd be how many hours you need. So we have capital L is revolutions. So capital L is revolutions. And that's typically not how you'd think of something in your plant. You'd think of script L, which is how many hours you need. So this is typically the one that you're looking for, is you have how many hours do I need this thing to run between failures, and then you set that number of hours slightly larger than your normal routine maintenance schedule, and then basically you have the conversion from revolutions to hours here, assuming it's in revolutions per minute, and n equals revolutions per minute. In most other texts, n is capitalized for revolutions per minute, but so just to make you aware, that's not a factor of safety here. N in this equation is not a factor of safety. It's revolutions per minute. And let's see, what else can I say about this? I think that's about it. Equation 11.3 again, it's going to be used. If I were to make you find one equation in the whole chapter and use it, that'd be it. It's in one of the main example problems we're working on. So, and here we go. There it is, right there. Here we have an example, and example 11.1. Definitely you want to look through this one. They have a SKF bearing, which rates its bearing for 1 million revolutions. So that means L sub R equals 1 times 10 to the 6th. And you desire of a life of 5,000 hours. That means, sorry about that, L sub design is 5,000 hours. So that's how the two different L's work out here. And then they give you the RPM and the actual load and the reliability. So N, in this case, N is 1725 RPM. The design load is 400 pound force, and reliability, this reliability of 90%, that's basically telling you that your load rating you can use as a L10 life. So sub R means rating, sub D means design. So this means rated or rating. This means design, what you're trying to do. So that's why they have the L10 equals LR here, because of that 90% reliability that I've circled. And then they have the conversion from revolutions to hours, and they figure out from that, they give you the design load, F sub D, that's a design load. They give you this top part here is going to be 5,000 hours. This is 5,000 hours times 1725. This is 5,000 hours, 1725 RPM times the conversion factor over 10 to the 6th cycles. And you've got your design load in there. And this is your answer in two different sets of units. And so that's what you'd search the catalog for. That's a pretty straightforward example. I'm going to cut this here now because it is actually bedtime for the little one, and I think that was probably about 30 minutes or so of lecture. So I'm going to reattach the keyboard here and continue chapter 11 with, actually, I guess I can cover this slide still, because it's basically saying we're covering sections 11.4 topically only. They're talking about bearing life as a probability function, and we're not really going to do that. They make reference to the Weibull distribution, which is very well utilized in this book for fatigue applications, and that's why it shows up here for rolling element bearings. But it's really unlikely that you'll be tasked with concentrate on that box. It's really unlikely you'll be tasked with making these kind of calculations in your career unless you technically specialize throughout your entire career on bearing selection and design, which is probably really unlikely. Like I said, I've done a PhD on rolling element bearings, and I don't even do that stuff. So I'm pretty sure you won't either. So that's why I'm kind of skipping it. But I do have some good advice for you on this. If you need this level of detail, start by calling the OEM for technical help. And most importantly, you can skip examples 11.2 and 11.3. That's going to conclude part 1 of this lecture on chapter 11. I'll get to it with the next part shortly. Thank you.